Thank you. Good morning. Today I will talk about bio-inspired front end with dynamic and spike-based component for speech recognition. And this work is in collaboration with Professor Rolf Mueller at Virginia Tech, who just sit over there. And the traditional approach uses the static periphery, microphone, and a computer, big or small, for the speech recognition. For example, the popular Echo and can play jazz through the Alexa. And I think most of the people probably have this at home. It worked very well in the clean environment. However, when there are multiple speakers are babbling, and the Alexa will get confused. And our goal is to integrate the brain-inspired computing with the bio-inspired periphery. And previous speakers talk about learning from the nature. Here we have an example of the learning from nature. And Professor Mueller's team have discovered that some bat, the ears change shapes when receiving the echoes. And they also designed the deformable robot ears, which can be used for the receptor for dynamic signal processing. Let's look at the ear motion. The bat with the deformable ears looks like this. That's the original speed, and that's a slowed down version of it. While the Professor Mueller's team designed some periphery which can also mimic the bat ears. And it's not just physically mimicking, and they are able to figure out the bat sonar, navigate through the complex environment, for instance, the dense forest, by injecting the direction dependence signature into the echoes received from the target, for instance, some prey. And our work is not so much into the ultrasound domain. We are more interested in the speech recognition. We are thinking if it's possible to look into the application for the of the bio-inspired periphery for the speech. Here is the diagram which shows, the top one shows the traditional speech recognition approach, goes with the static speech signal processing and the traditional acoustic feature extraction, for instance, the mild frequency substrate coefficient approach, and that's formed the front-end approach. Then most of the people have been working on the classification and output readout of the result. And our focus here will be mainly on the front end. And we are thinking of utilize the dynamic periphery inspired by this deformable bat ears, and also the cochlear filter. In addition, we also use the spike-based stochastic masking to finish up the front-end approach to see if it indeed can separate the noise from the speech. And of course, the future work can be done regarding the neural-inspired adaptive classification or whatever, and those are not in our talk today. To implement this concept, as we mentioned, we have the static raw signal speech data, and we dump into the dynamic periphery from the robotic bat head. And this robotic bat was able to modulate the signal and make it looks like so much different from the static signal. And after this, we feed the dynamic signal into the cochlear filtering and then get the cochleogram. And this is one of the features. On top of this cochleogram, and we also use the spike-based modeling to form a stochastic mask. And we take the dot product of the stochastic mask together with the cochleogram and get the spectrum on the top. And this whole process are purely front end. And we still use a traditional classifier at the back end to see the speech recognition rate. And the major difference between the traditional feature extraction and the bio-inspired approach are the following. The traditional way used the triangular MEL filter bank and the coefficient values as features, while the bio-inspired approach used the cochlear filter bank and the firing probability as a feature extractions. Of course, there's tweaks in terms of adding the mask of the spike-based masks. If you are interested, we also have the poster, so I can tell you the details about this comparison. This is the comparison of all the, oh, sorry. Why? Oh, okay. All the different speech signals and the speech signal and the different feature representations, traditional way and the bio-inspiration, to compare the static speech and the dynamic speech with and without babbling noise. And the results of the speech recognition and clearly see the degradation at noisy environments with the static data and the traditional feature extraction. When we add this dynamic component into it, and it looks somehow less degraded. And this seems to be encouraging, but not enough. And what we try again is try to do the cochleogram as a feature representation. And this is the raw data, and this one is the dynamic data. And this clearly shows some sign of improvement, although in the very noisy environment, it may cross point. And finally, the result from the spectrum which we come up with looks even more encouraging. Clearly, this one is the this one is the raw data. Here is the dynamic data, and clearly we see the noise robustness from this spectrum purely from the front-end integrations. And in summary, we think we are able, sorry, it's always slower. We are able to, it's again disappeared. Sorry. Again, we are able to integrate the bio-inspired front end, including the dynamic sensing and cochlear filtering and spike-based masking for speech recognition. Well, the pilot data from the dynamic periphery shows clear the noise robustness, and we think it's due to the fact that the dynamic periphery inject the direction-dependent signature into all the signals received. And the spectrum seems to better represent the information encoded by the dynamic periphery. And we think the last one, the front-end integration clearly help to improve the back-end classification, where most of the people are doing, especially in the babbling or the noisy environment. Thank you very much.